We want to minimize f, x, and x is in a constraint set C. Last time we talked about this, that means x is inside the non-negative orphan. So this is easy to deal with. What if we have some very complicated C? So that's the focus today. And I'm going to use the L1 norm ball as an example. Recap last week is that we do this by doing something called projected gradient descent. So the new point is current point minus step size, which is a number, gradient. That means you need to know how to find the derivative. This point is possible outside the C. Then what we do? We project it back to C. That's the idea. So if we do this every time, the xk plus 1 will go down. So that means we have this. This is for any k. And every x for whatever k is also in C. Then if we have this, now you see, and let's say the last point is 0, then you have something go down to 0. And you run it infinite number of iterations, you get 0. And you solve the problem. And today's focus is what if this C is some complicated thing. For example, L1 ball. That means we're going to talk about the projection sub C thing. And then in this notes, I write it as PRJ. That means I spell the whole thing. So what's that? So we have a point y. So y is given. Two-dimensional coordinate system, okay? So this is a vector y, okay? Or I just draw a point here. And then what? We want to project onto a non-empty, compact set S, okay? So why we need this? Because if S is empty, we project to vacuum. That means no solution. Compact means closed and boundless. You have a set, you can draw boundary. What is not compact mean? I just give you an example. Minimize x, find the smallest x, such that x larger than 3. So this is what I have a line here. And then I have a number 3 here. My x is larger than 3. So that means my set S actually looks like this. The funny part is exactly occurring at this point. Is 3 included? 3 is not included. This problem actually have no solution. Why? 3.1. Then I can say, why not 3.01? Then I will say, why not 3.001? Then if you accept this, I can always give you another solution. So this is the problem of not being compact. What's compact? Compact means closed and bounded. So this is open, it's not closed. So that means you cannot draw boundary. So if it's not bounded, that means you can go to infinity. So that means closed and bounded means it's not, you cannot go to infinity. That means you have a limited set and you can draw the boundary. So this is the meaning of compact, okay? So now we call, in this notes, I use the notation S, okay? So it's the same thing. Then this is saying that I have a projection of my given y. So let's say my S is like this, okay? My S is like this. Then this is y, this is y. I want to project this on the S, which is this shape. Then it will give me, last time I talked about it, you draw a circle until the circle touch the set. So it will be, this particular point will be my x hat here. So this x hat will be the projection. That means the output. This mapping is a what? A point-to-point mapping. So please be careful. Projection is a Rn to Rn. It's not Rn to R. Minimizing something is a function f. It can be vector input, so it's Rn. And output of a vector input function is a number, so it's Rn to R. So that means min f is something, this f is Rn to R. So minimizing this thing, give me a number. So this is Rn to R. But projection is a Rn to Rn. So it gives me a point, it's not a number. By what? By solving this problem. Find among all the x inside the S. So this part means look at all the yellow thing in this region. Because this yellow thing means all the x inside a set S. So this yellow region. This green part means find what? The smallest circle that the radius is x minus r, right? So that means you find this thing with the smallest circle such that this is true. So let me recap. You have a point y here, and then you draw a circle. What is this circle? This circle is all the y1 minus x1 square plus y2 minus x2 square plus so on. This, right? This is an equation of a circle, right? And then you have a radius r, right? So basically this thing is saying that the picture is you have a radius r circle, and this is more general than a plane circle. It can be a higher dimensional circle. You can call it hypersphere or sphere. That means you have an n-dimensional circle, and you have a radius r, and then everything on this black solid line is equidistant to your y. And then this exactly is the value, the green thing here, x minus y 2 norm. Because you remember 2 norm, you have to take square root, right? So this is exactly the radius. So basically this means what? Find a radius, smallest radius circle touching the set S. That's it. That's simple. This is the idea. And if your point y is inside the set S, do you remember what I talked about last week? It gives you back the y. So that's the idea. So this is the introduction. So here now is the main point. What happens if my set S is the L1 norm ball? So what's L1 norm ball? L1 norm ball means this. What's this? It means absolute value of all the components summed together smaller than 1. So L1, okay, let me recap what's L1 norm. So if I have this x, vector x, L2 norm is what? Is x1, the component, okay, all of them take square until the last one, and then I take square root, okay? So you can think of it as what? You can think of it as xi, so all the I component, I take a summation sign, okay, for all the I, okay, and then what? Power, and then after I do the summation, I take 1/2. So actually this is called LP norm. So if I replace the red thing, okay, I replace the red thing, if I replace the 2 by other number, p, then I will do the same thing. It will be xi p power. You should take the absolute value before the square. So I have absolute value p and then 1 over p. So what happens if p is 1? If p is 1, no power, no square root. So it's just a bunch of absolute value add together. That's why you have this. So L1 norm is just all the absolute value inside a vector add together. Then now what is this? This is saying that, well, I'm saying I have an S. S is a subset symbol of Rn. That means I need a set. L1 norm is not a set. L1 norm is just a number. It's a value, right? So I'm saying all the x such that if x smaller than 1, then I have a set. So let's first draw what is this picture looks like. So suppose I have R1, one-dimensional case. Then my x is just one number, right? So if my S is all the x such that what? The absolute value x smaller than 1. So it will what? So for one dimension, it's just line segment. Then what about two dimensions? So if I have R2, so n is 2, then I have two-dimensional space. First, two-dimensional space means I have x, y, right? L1 norm is what? Absolute value x plus absolute value y, right? Then of course, first of all, I will have this region because this is exactly this. This line means I have the same thing as what I have in one dimension if all my y is 0. Well, this is the line y equals 0, right? So of course, if I have this line, I should have this line here. Then I have the same thing. I can have y is not 0, but x is 0, right? Then by the same logic, I will have this line, okay? So I will have a cross here. Now, here's a funny thing. I can have 0.5, 0.5, right? 0.5 and 0.5, I take absolute value, sum together is exactly 1, right? So 0.5, 0.5 is okay, right? At the same time, 0.3, 0.7 is okay, 0.1, 0.9 is okay, right? Which exactly is this part. So in the end, if you consider all the possible cases, I also have all the line here. But I can also have 0.10, right? Because this is the L1 norm is smaller than 1, so I also have here. So in the end, I will have what? What's the L1 number? It's a diamond. You can think of it as a square, but you rotate 45 degrees. So this is L1 number. Then this is 2 dimension, this 1 dimension. What about 3 dimension? Okay, now I will jump. So 3 dimension, you have a pyramid. Okay, you have a pyramid. Okay, and then imagine you can see through the paper. So you have a pyramid. Then this is R3 L1 number. Okay, so this is what? This is like what? If I have this projection thing in 2 dimension, basically it means okay, I have a point here, y. This is my coordinate. My L1 number is something like a diamond. So basically, it's like find this guy. Okay, now this is interesting. For the thing we talked about yesterday, not last week. If this is our non-negative orphan, that means R plus. Projection is very easy. Why? Because it's always 90 degrees to this thing, right? Unless you have here point to this point. But now we have an angle between this plane and the point. So suddenly projection onto this S is not trivial. So that's why you need some additional mathematics. And the additional mathematics is called optimality condition, which is called Lagrangian multiplier. So, okay, this part done. I just said what I said, okay? By the way, let me just recap what is L2 norm. Okay, L2 norm was L2 norm. If an x vector x is just this, okay? Because absolute value of the square is the same, right? So I have this. Then let's say we have 2-dimensional case. That means we have our vector is x, y. Then our L2 number is exactly x squared plus y squared. So it's a circle. Okay, so about 3D, x, y, z, then you have a 3-dimensional ball, okay? And then that means L2 norm is a sphere, okay? And just to let you know, what about LP norm for p larger than 3, and then p smaller than 1? So this is just some figure, okay? So I have a bunch of coordinate here, okay? I have a bunch of coordinate here. So this is L1 norm. L1 number looks like this. L2 number looks like a circle. What about L infinity number? You can p go to infinity, right? Let me tell you, L infinity will be a square like this. And then what will be in between? You can imagine I blow air into this thing, but limiting it within the unit box. So you can think, okay, this is hard to draw, but I try my best. So it will be, okay, something like this, okay? You just imagine. This is, let's say, L7 norm, okay? I don't know what this looks like, but anyway, this is L infinity, this is L2, okay? This is L1. Then what about L half? L half will be, yeah, something like this. What about L 0.00001? 0.00001. It will be, okay, like a star, okay? You can imagine, okay? Then what about L0? L0 will shrink to the center, okay? So you can think about this. So this is just a picture, okay? And this is convex set, this is convex set, this is convex set, this is convex set, this is not convex set, okay? Anyway, now we have this problem. So I given a y, find the smallest distant x. This x have an L1 norm smaller than 1, that means it's inside the diamond, and the radius between my y and this x is smallest, okay? So this is the problem. This is our problem, I call it P, okay? Now, here's a very common trick. So I have P, this is L2 norm. So I have a coordinate here, this is 0, 0, and L1 norm is this diamond, and I have a y here. And then you remember, right? This circle are the equidistant circle towards my y, and the radius between the circle and the y is exactly the distance, okay? So this circle is coming from the 2 norm. That's why I have a 2. That's why I circle. This diamond is the 1 norm. So that's why this figure have 2 things. A circle thing come from 2 norm and a diamond from 1 norm. And let me tell you, funny thing. What happens if I have L1 norm? Okay, that means x 1 norm smaller than 1, and I also want this is 1 norm. Then the picture will be this one become a diamond. So that means I will have. So first of all, this is a diamond for this part. Then let's say my y is here. Then what will this look like? I will get circle in this case. Then what's projection in this case? It will be same. You find the circle with the smallest radius touching the region. And of course, this is not circle. These are some crazy shape, but anyway. And then you can change this to what? 2 norm, 3 norm, p norm, less than half norm, then you will have this kind of funny picture. Let's say I have a half norm, then you have this kind of thing, and then yeah, that means in this case, this is the point, you get it. Of course, this is rare, but anyway, this is the idea. Okay, so now I want to solve this, but because L2 norm, this term, have square root, we don't want to deal with square root, so I put a red thing, 2 here, and I put a half here. So this is okay. Why? Let's say my function is simple x squared. If I multiply 9,000 in front of my function, my curve looks like this. Where is the minimizer? It's the same point. If I multiply my function by 0.0001, it looks almost like a flat line, but same, the minimum point is still here. So arc is invariant to multiplying a number here. So that's why I can always put a number I want, okay? And then why put half here? Because after differentiation, the 2 come out and cancel it, that's the idea, okay? Then why we put this red thing here? Because we don't want to deal with square root. Then that means this is what? This is the optimization problem. What's this optimization problem? This optimization problem is this form, minimizing f, and now this f is differentiable. And then we want x inside set S. So this is this, right? Previously, this is a very easy set. So I can just do project set. But now this is not easy set. So we need to do what? We need to introduce new variable called Lagrangian multiply, lambda. And then we need to consider something called KKT. KKT is just three people's name, okay? And then what the heck the idea is this? So suppose I have x. This symbol star means op. That means best solution. So I put an x star means this is the solution. So I can say x star is definition defined as arc mean of this. So this is the guy that minimize this thing. Then what is optimality condition? It's saying that what will happen to f, gradient of f, constraint set, what happen for this kind of thing if I reach optimality. So this is the idea about optimality condition, is that now I want to solve this, but I don't know. Now I assume I know this guy, and I do it backward. I look at this kind of condition, see whether or not it gives me some hints on how to solve this. That's the idea. So first, we will need to form something called Lagrangian. So what the heck is this? Let's say I have min f, I have a condition that 5x smaller than 0. What is Lagrangian multiply? I got L here. Okay, very simple. I just add these things inside. Then what? Then I need to put a scaling parameter here. I put a lambda here. So this is exactly Lagrangian multiplier. Actually, this is something called penalty method. Let me explain. So I'm going to use an easy example to explain why this works. Okay. So suppose I have to minimize x squared. Okay, x squared half x squared. So I want to find the smallest value here. We know it's 0. But now due to some reason, I want my x larger than 3. This is 3. So I can only allow this region. So what I'm going to do? I ignore this. If I ignore this, that means this line extend to all the line. But I want this line to be kept. So I'm going to say that I'm going to do something like this. Okay, what? I add something here that if this is violated, function value increase. So this is called penalty. That means what? That means I need to design a function f, and a function p, I call it p, okay? If this is not true, then this guy gives me big number. And if this is true, this guy gives me small number. Why? Because I'm doing minimization. I want things small. So if this guy I minimize to small, and this is designed such that this is true, give me small value, then I have fulfilled what I want, right? So you have a constraint, x larger than 3. This is the original problem. Now I create another problem. I call it P2. This is P1. P2 have no constraint. Any x is okay. So you have the original x squared. Now you add a penalty function. This guy is trying to encourage this is true. And you design a P to encourage this is true. By what? If this is small, this P is also small. This P is also more means this. So this is the idea. Then this is a P, right? You can also scale these two things, right? Because this is now two functions. So you can think of this like this is F and this is G. So if I put a 10 here, it means what? It means this guy minimizing this is 10 times more important than minimizing this. And what happens if I put a 100 here? It means minimizing this is 100 times more important than this. How do you see this? Because in gradient descent, suppose this is my function. When I do gradient descent, I will have to take the gradient of the whole thing. Then this 100 will stay with the gradient on this part. And this 100 will scale the gradient. Okay, so I will have this, right? And then I will have a 100 here. Of course, I have a step size, but this 100 will say that in this sum, this guy is 100 times more important than the G. So the gradient direction, that is how I move my X, will be dominated by my F, right? So therefore, this scaling actually is like I have an arrow and I need to force my gradient descent to go to the direction favorable to the one with the big number. So that means if I have the general problem like this, okay, if I have this, let's say equal 0, then I can say my penalty function is I want this to be equal to 0. That means if this guy is non-zero, I don't want it, then I can say my penalty function is exactly the norm of gx, okay? Because if this is 0, then norm is 0. Then I have a scaling. If this is 1, I mean this one have an equal weight. If this is 9,000, then this one is 9,000 times more important than this one. And this is called penalty parameter. It's a weight. And then in Lagrangian, it's the same. I have my function. and my constraint. Now I put my constraint into my objective with a scaling parameter. So you can think of this as what? As a penalty problem. So if this is violated, then let's say x is 9,000. If x is 9,000, the L1 norm is 9,000. It's not in the diamond. The norm is too big. Then this term becomes very big. But I want to mean this, right? So therefore, it's not good. Then what about this lambda? Lambda will be a number. That means it's the best parameter to balance these two terms, which is also an unknown. So in other words, you cannot just say, oh, I have a this and I put 10 here. Actually, this lambda will also change. There will be a best number, lambda, such that when you solve this problem, it's the same as you solving the original problem. So you can think of, I have an original P1. Now I put the constraint into my object function, I call it P2. There exists a magic lambda such that if I solve this one, it gives me the solution this one. So therefore, if I solve this one, using this lambda, I get back to here. So therefore, now this Lagrangian problem have two variables. Instead of x alone, you also have a lambda. So lambda is also unknown. If you fix this lambda 10, 20, 40, you are doing penalty method. Lagrangian is saying that this is also unknown because we also want to know, is it 10, is it 20, is it 40? Now with this, we have this one, add this one. Now I distribute lambda inside. I have this plus this and this. Okay, then what? For general problem, mean f subject to g, okay, you have a Lagrangian, which is f plus lambda g. What are you going to do? You're going to do the following. This guy is optimal. The best x will be exactly when you take the derivative of L, give you 0. And exactly at the same time, take the derivative with respect to lambda, it also give you 0. So you want this to be the case. But now we have some funny thing. We have an L1 norm, which is not differentiable. So we need to do something more advanced than standard differentiation. Absolute value is like this. Its differentiation before 0 is -1. All the slope here is -1. After 0, all the slope is +1. What happened here? I can now tell you, is everything between 0 and -1 and +1. And where does this thing come from? The idea is this. If I have a function that like this, what is differentiation? Differentiation is slope, right? That means I have a point here. The slope at this straight line is the differentiation at this point. The slope at this line is the differentiation at this point. Then the slope at this line, which is exactly this line itself, is the differentiation at this point. Then what about this point? Well, if I use this idea, I have a function. How do I find the derivative? It's just at a particular point, I find a straight line under my function. Then the slope of this straight line is the slope of my function. Then I'm going to say any slope that touching this point or the slope here are the differentiation, the derivative of this particular point. And now you see, for this particular point, you have a bunch of slope. Unlike the other point, you only have one slope. So that's why at 0, you have multiple derivative value. So this is a set. And because now we deal with set, so we are no longer saying A equal B, but we are saying A within the set B. So we now have this symbol. So therefore, this is the case when everything is differentiable. What happens if we have something not differentiable? We write this symbol. This looks like partial derivative, but now this is sub-differential. We talk about sub-differential later, but today I just introduced to you. So this is called sub-differentiation. Okay, I don't spell the whole word. Okay, make a spelling mistake anyway. So what I'm going to do, I'm going to do the same thing. I just replace the triangle symbol by this partial derivative symbol. But anyway, this is not partial derivative. This is sub-differential. So I will have this. But now this is a set. Because why? At 0, multiple value. So this is a set. This is 0. 0 means one number. So of course, I will have this. So it's not equal because it's a set. So then, because of this means what? Slope is 0. Why? Because if you have a minimum point, you know slope is 0, right? So now I have this. What's the minimum point? 0 is one of the particular slope here. It can be this, right? It can be this, but it doesn't matter because 0 is one of the particular slope here. So therefore, I will have the sub-differential of this thing and 0 belong to the sub-differential of this thing. So, okay, now I'm going to explain this part. This part is this part, right? Basically, I just split all the element by element. Why? Because what's this thing? This thing basically is x1, x2, blah, 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 vector minus y1, y2, blah, blah, blah. And then this is a vector, L2 norm square. What's L2 norm square? This guy's square plus this guy's square plus this guy's square. All the bracket is just one particular element square, right? So I have this part. Okay? What's the absolute value? No, what's L1 norm? L1 norm is just absolute value for all the I. Okay? So this part is this bracket. This lambda have nothing to do with this, so I have this term. Then what's next? I'm going to do derivative of this guy. Derivative of this guy, I can differentiate, right? So this one, no problem. But absolute value, as I said, it is not differentiable by 0, so I need sub-differential. But anyway, I call this thing my small l, okay? Then you notice that each of the small l have only one xi. So I can split all of them. So therefore, my vector x is a what? is a x1, x2 thing, right? Then if I do the partial derivative of my thing, that means I just need to partial derivative each of the Li, right? L1, L2, L3. So that's why I have this term here. These are all the x, and then we also have the lambda, but I didn't write it here, okay? Then this term is just one particular term here without the summation sign, and now I do the sub-differentiation. That means I put this symbol on this big bracket without seeing the summation sign for one particular I. So I have this thing. And then what? Sub-differentiation become normal differentiation if the thing is differentiable. So this part can go inside. Okay, let me tell you one important thing. Year 1 or high school, you may know that, okay, this thing is a df dx plus a dg dx. You can split it. Let me tell you, this is not true for sub-derivative because in some situation you can't do that. But now in this situation you can. So in other words, this process behind it is some master level PhD mathematics. Don't underestimate it, okay? This is not true in general, okay? But now you can. So that means I can do this. Then what? This is differentiable. So you will get the classical derivative. That means 2 come out, and then these things, that means this part will be xi minus yi. Okay? This part will be what? Lambda, the absolute value. You take the subgradient or subderivative. So what's that? Let me recap. It will be what? It will be everything after 0 is 1 because the slope of this line is positive 1. Everything before 0 is negative 1 because the slope of this line is negative 1. Everything exactly in 0 is an offset between negative 1 and 1. So the subderivative will be what? The subderivative of this absolute value will be plus 1 if x larger than 0, negative 1 if x smaller than 0. If x is exact 0, it's a set from negative 1 to positive 1. So this is now the thing. And this thing can be written as psi function. Okay? So I will write this as psi function. Therefore, this is what I said. You can put this inside, you can have this. I have a 1 here, 1 is subderivative linear here. This is not something trivial, okay? And then step 2, this guy is differentiable, so I can do it using the classical derivative, which is just x minus y, okay? And then this guy, okay, lambda can go out, I have this, and then this is called psi function, which is again this thing. This is not a function in the strict sense, because why? Because you have 1x give you more than 1y. But I'm just writing this as a symbol, okay? So you have this thing. Then what? This term, the slope is something like this, okay? Now, let's go back to the very beginning. I have this Lagrangian term. It's my f plus my g. So I've written like this. So this is the same thing as the previous slide. Okay? And then what's the optimality condition? The optimality condition is 0 belong to the gradient of my L. So 0 belong to the gradient of my L. Gradient is the slope. Why this is a belong to? Because this is now a set. Okay? Each guy here is a set because of the absolute value. So after the calculation, we found that 0 belong to each of the particular subgradient, which this particular subgradient has this form, okay? So therefore, 0 belong to something that looks like this. So now here's the funny thing. That means I can put a y here, then I have y belong to xi plus lambda psi x. So what is this? This is saying that, suppose x is solution. Y is my input, right? Y is the point I want to project. So I will have this funny thing. I want to project my y into this set S. And this point is as x. There will be an equation relating this x and y, which is this thing. So that means if I have some way to write my x as a function of y, I got how you can project it to the sphere, right? And this is the non-trivial part, and this is the detail. So that means I now want to find a way to write from my input, give my output. Y is the input, okay? So how do you write this thing? This is the idea. This is a function, y written as a function of x. So you want to write the opposite, x as a function of y, which the solution is this. You have no way to know how this comes from. But here's the trick. So this is a coordinate, okay? This is xi, so I have something that looks like this, okay? This is sine y, so suppose lambda is 1. Okay, suppose lambda is 1. Sine x, what is sine x? Sine x is, again, this, right? Then if these two add up together, black add red, what happens? So think about it part by part. For anything after 0, that means positive, I have this thing, I basically plus 1. So positive part is this. Negative part is this one minus 1. So this is the negative part. So that means this is the curve. This is the curve, okay? How do I get x as a function of y? I flip it along this thing. Then I will get something that looks like this. Then this is what? The function writing x as a function of y. Then this is this thing. So what is this thing? Okay, let me go back to here. I have this function that looks like this. This is sine y. So basically it's this, okay? Absolute value y, just this, right? Minus lambda is just 1. In our case, it's constantly negative 1, okay? What is this bracket thing? This bracket means if it's negative, get it to 0. So what is this part? Without a bracket. So this part without bracket is absolute value y minus lambda. So it will be what? It will be this thing plus this thing, basically I move everything down, right? I move everything down, so I have something that looks like this. Now I take the bracket. So I take the bracket. So this part is gone. This part is gone. This part is gone. So or I use color. Green is gone. And green becomes this flat line. So now I have something look like this. Okay. Now what? This part, the sign is negative. I flip it down, I get this. So I flip this down, so I get this. So therefore, projecting a y into unit L1 norm ball, the closed form expression is some funny function that looks like this, which this is lambda. I'm now saying this is 1, but we actually don't know. But suppose you know, then the formula of projecting y into a diamond is what? You put your, so y project to diamond is, you have y, take the absolute value minus the lambda, which is an unknown, but let's say we know it now. And if this guy is negative, becomes 0. If this guy is positive, keep the value, but then we have to put it with the sign. So basically it's this thing. Okay, you see, this thing, you can, in no way you can explain this in one sentence. This is this curve, because this is what? It's a piece-wide linear curve. You have 3 pieces. 1 pieces, 2nd pieces, 3 pieces. So this thing actually is 3 cases. So this is a split function. Okay, split function. So that's why you cannot explain it in one sentence. You need 3 sentences to say it. So it's like for very, very positive y. So let me say this. So what is this meaning? You can think of it like this. This is my coordinate. It is same as for very big. So think of it like this. For very, I'm going to draw here, but now I don't draw this in. So this is the y equal x, right? This is equal linear. This means what? For very big value of y, the idea is I just shift it by lambda amount. Yeah, so basically this is going down lambda amount. For y that is smaller than lambda, everything here go to 0. And this part is the opposite sign. It's the same thing. Yeah. So this is the idea. This is the idea. So that means what? I have a vector x and y. It is a bunch of numbers, y1, y2, y3, y. If some of them are very small value, they become 0. If those values are very big, I just slightly going down a little bit. Okay, that's the idea. So this thing have a zeroing effect in the vector. So in other words, if you do this for a vector, some component will become 0. This is called sparsity. Okay, and this is the expression. So I just explained to you the idea. So I have this Lagrangian stationarity. That means optimality is 0 belong to the subdifferential of this thing. So I just tell you, this is telling you get this funny formula. Okay? And then what is this thing? We need feasibility. That means x L1 norm smaller than 1, right? So we have this one. This one is the same as this sentence, right? Okay? And then this thing, let's imagine, if I minimize this thing, then this is what I want to minimize. This will go down as small as possible. This one becomes 0. Then I will have this, right? Then for this thing, I will have what? I will have either lambda is 0 or this bracket is 0, right? If lambda is 0, then this is free. I mean, x can be any number. But if bracket is 0, that means norm is 1. So I have 2. And what is 4? 2 feasibility. Lambda need to be a positive number. Because if lambda is negative, then I just make my x go to infinity. This go down. Right? Because if this guy, let's think about it. If lambda is negative, then I have something subtraction. How do I make this thing go down? I just make this as big as possible. Go to negative infinity. But I can't. So therefore, lambda has to be positive. This is one explanation. Okay? Then I will have this. I have 1, 2, 3, 4. This 4 sentence is called KKT condition. And this is the expression of how you get an x. But I said we need to know lambda. So how are we going to get lambda? We are going to say that we try to squeeze this free line into lambda. Then we will find what is lambda. Now this part is the analysis of how do we get lambda. So we have first case, lambda is 0 and lambda is larger than 0. So we have lambda is 0, or this case means lambda larger than 0. So if lambda is 0, then this thing gone. Xi is just sine y, y is absolute value. Absolute value is always positive. So I will have this. And sine y, y is y. Because this actually is the definition of sine. So xi is y. And then if xi is yi, since I have this is true, this small line is always true. Xi is yi, that means yi is smaller than 1. This means what? This means this is the case when y is inside the set. If y is inside a set, then the absolute value of y L1 norm is smaller than 1. Then in this case, lambda is 0. Okay? Then what about if lambda is larger than 0? That means not this case, but this case. Okay? So now we have finished this case. We have finished this case. Okay? Then now what about this case? Okay? Then lambda is 0. Then this is wrong, right? So we have this thing. Then x1 L1 norm is 1. So all the absolute values sum to 1. And then this is equation 1. I now what? Put this equation here. I have expression of x, right? All the here are just this thing. I squeeze this in. I will get something that looks like this. Because this all sum to 1. So y1 for sine y and then do this. And then y2 do this. y3 do this. So on. Add all of them. Give me 1. I get something like this. Now this is the key. This means what? I have a formula to find what is lambda. Because y is known. Y is the given point. So if I solve this I know lambda. So these are the two cases. If my y, let me recap from the very beginning. I want to find y into a specific set. If my y is already in this set, I do nothing. Do nothing means this case, my x is my y. So done. The trouble case is what happens if y is outside. If y is outside, now lambda is some magic number. Which if I add this magic number here, this will give me the best penalty of this on x. And then what? I need to solve for the what? For the lambda. Then I can put this lambda here. I get all the x. So I just rearrange term here so that this gives me an expression on lambda. So you have another three cases, right? These are just a bunch of analysis. Because of time, I will skip it. Then in the end, you will get some expression that looks like this. That means if you analyze all the possible cases for the y, you get three cases. So if you solve this equation, and then you plug the lambda into this expression, you solve the projection problem. Okay, now we will go to how do you solve this. The equation I just said is in this form, right? It is in the form of, you have a constant c multiply a plus b minus d, right? Something like that, right? If I write this thing as a bracket with a plus, then this expression becomes something that looks like this, right? So I'm going to talk about how to solve this, okay, for any a, b, c, d. And then now let's look at the geometry. What's this? This is real U unit. Real U has nothing new. It's just some old stuff with a new name. Okay? So I have some A1, A2, B1, B2. Okay? So suppose I don't put the bracket. Then AX plus B is just straight line. High school geometry. Then suppose I have a plus. Plus means what? Anything below the y-axis go to 0. So this part become 0. This big part become 0. Then what happens if I add these two lines? Then at this point, both are 0. Okay? At this point, purple is 0, but orange is not 0. So this part is orange. What about after that? We have two parts. Then you just, that is very simple. You have an angle here, right? And you have an angle here, right? You add the two angles, then you get this. So therefore, you have some function that looks like this. Okay? So it's a piecewise function. Okay? Then what? Now we are saying, find this equal to d. So suppose d is here. Then basically this question is asking, where is this guy? That's it. And if d is here, then x is 0. If d is here, there's no root. There's no root. So this is an equation or polynomial. D means you have something like this, and you want to find in which point the x and the horizontal line and this orange curve cross each other. Okay. So these are some terminology. Blue thing is my funny function, my piecewise linear function. My d here is 1. Is my red thing. So what is the solution point? The solution x is actually the x coordinate of this red point. Okay. Then what about this kind of point? This kind of point is where the behavior of the function change. It's called breakpoint. So I have two breakpoints. So that means this thing can be written as 3 parts. And if I have one breakpoint like this, that means this thing can be written as 2 parts. That means if I have many breakpoints, I have a split function with many parts. That's it. Then how do you know how this function has root or no root? This is, well, this is exactly the same thing as, oh, you have 2 root, high school. You have no root. You have 1 double root. Something like that, right? So no root. Okay, if this is 1, this is 1. This one does not touch this, so no root. This one, it touches infinitely many root. And then what about this? Exactly 1 root. What about this? 2 root. Okay, so that's the idea. Let's look at how we solve it. So suppose my first F1 is the blue, it's like this. Okay, and my red is this. Okay, my red is this. Then yellow is blue plus red, which looks like this. Okay, and my D is 1. So I'm trying to find a cross point with this line, which is this point. Okay, so that means this x gives me the root. Okay, so how do you solve this problem? Very easy. For each segment, you check whether or not this segment cross the line, and that's it. So what you do? First, you find the expression of this part. Then what? You see whether or not this part cross with this line. If this part cross with this line, that means this function equal to 1 have a solution. Then it gives you a solution. And solving this problem, that is testing whether a part have a solution, is just some y equal mx plus c decision problem. You know the slope, you know the crossing point, you know the y value, which is 1 here. Of course, you can know whether or not there's an x. That means for this problem, you have n breakpoint, and for each of the line segment, you have the breakpoint in this form. You sort them. Then it means what? You have a bunch of this kind of thing. Okay, you have a bunch of this kind of thing. Okay, you sort them. Then it gives you this. Then you have segment 0, segment 1, segment 2, segment 3, segment 4, and segment 5. What are we going to do? Test, is this crossing the D Test, is this crossing the D? Test, is it crossing the D? Test, is it crossing the D? Okay, testing this. What's the worst case? You have to test everything until the last one. So the worst case complexity is n. Okay, sorting is n log n. So the worst case complexity is n log n plus n, and this becomes O n log n plus 1. Big O notation don't care about constant, so the complexity of the whole thing is n log n. So therefore, how do you solve projection onto simplex? You sort this A and B, and then you have an n log n cost, and then for each of the line segment L, you test whether or not it intersect with y1. How do you solve it? You basically solve the equation like this, which primary school or high school, okay? And the whole thing have a complexity of n log n, and that's it. And suppose you only have k non-zero in a C, because sometimes this C is a bunch of zero. Then you can even reduce to n plus k log n, because if you have k non-zero, then you have k log n instead of n log n. Because for those zero guy, you don't need to solve, right? Then you also have the n for the checking all the line segment. So this will be the complexity. And this is somewhere between between O n and n log n. So that means the best case you can do is O n, the worst case you can do is n log n. And this is something unavoidable. So that means if you want to project a point into this funny shape, what you need to do, here's the full story. You have the y vector, which is y1, y2, y3. First, you form this funny function. Yeah, you form this funny function. Okay, what is this funny function? I almost forgot the plus. Each of this part is a small l, is a line segment. It's basically something in this form. You have this a and b, you sort this value. It gives you all this breakpoint, and then in the order. And then, because you want the d is 1, you just find which line segment the L cross the 1. Done. Then you find the lambda. Once you find the lambda, this is x. Done. So you find the lambda, you find x. And x is what you want for the projection. That's how you project onto L1 normal.